In this video, the weak formulation of the steady Stokes equation will be derived. This problem here is the Stokes problem in strong form. In the first line, we have this PDE, the steady Stokes equation, in omega, in the region omega, which is bounded region in Rn. Divergence of u, which means that you have a divergence-free velocity field inside the domain omega. U is equal to 0 at Dirichlet boundary. Gamma t denotes the Dirichlet boundary, and the stress, the component of the stress, is equal to 0 at the Neumann boundary. Here, the boundary of omega is the union of the Dirichlet and Neumann boundaries. U is the velocity field, and it belongs to the vector valued h1 Sobolev space. W is the test function for the velocity field. It's h01 omega 2, which means it's the vector Sobolev space. P is the pressure in L2, belongs to the space of square integrable functions. Q is also the test function that corresponds to the pressure and belongs to L2. And F is the source term, which is vector valued function and belongs to the vector valued L2 space. So using this data, we will obtain the weak formulation of the Stokes equation. We will obtain the saddle form, and then we will give the discrete analog for this problem. Minus nu is the kinematic viscosity of the fluid, u is the velocity of the fluid, and p is the pressure. So minus nu Laplacian of u plus the gradient of p equals f. I multiply the left and right hand side by the test function for the velocity field w. Now I integrate over omega, over the rectangle. I impose integration by parts. Let's denote gamma, the whole boundary of the domain omega. And what I have here is w. I have this integral at the boundary minus the integral over omega of this bilinear form. So this is bilinear form here. Plus, then here I do also integration by parts. And I have here the inside the integral p divergence of w the omega equals the integral over omega f times w the omega. Now how can I write this? The integral over omega minus the integral over omega p divergence of w the omega equals, I have this function at the right hand side, plus the integral at gamma plus this boundary integral. We know that at the boundary we have two parts, Dirichlet and Neumann boundary parts. So we have integral over the Neumann boundary plus the integral over the Dirichlet boundary. Now we have imposed homogeneous Neumann boundary conditions at gamma n. So this integral vanishes, is 0, and we know that the test function belongs to H01, so it vanishes at the boundary gamma d. So from here, we only have the contribution from integral f times w. This is the first relation. Now we know that the divergence of u is equal to 0. We multiply by the test function q, so minus the integral over omega, q divergence of u is equal to 0. Now we combine these two relationships to get the following saddle problem, the saddle form, basically. And here minus the integral over omega, q divergence of u, the omega plus 0. We can write it in matrix form like this. And at the right hand side, we have the contribution of this integral. Integral over omega, f times w. And here we have zeros. If we discretize this problem with finite elements, here we have the matrix A, which corresponds to this bit, B transpose, which corresponds to this bit, B, the matrix that corresponds to this integral, and 0. And here this is the right hand side f. So the discrete form would be A, B transpose, B, 0. It's a block matrix. And here you have the velocity and the pressure, the vectors of the velocity and the pressure, and here you have the right hand side. This is a block matrix. You can write it as S of U equal F. You can use Q2, Q1 discretization, finite element discretization. Q2 for the velocity, and Q1 for the pressure.